All right, in this chapter we're going to take a look at graphs, and we already looked at graphs a little bit in the first chapter by using a relation. We used a graph to kind of be a visual representation of some relation. In this chapter we're just going to look at graphs and graph theory even outside of that context of relations. So we define a graph to be has a finite set of vertices, so we have a vertex set, and a collection of edges. And these edges really are just two-element subsets of V, of the vertex set. So if you have an edge, it has to connect two vertices. So we just indicate each edge by listing the two vertices that it connects. An element of that set is called an edge, and the graph we denote by G and then parentheses V comma E. So there's a graph G that consists of these vertices and these edges. The elements A and B of V, or the vertices A and B, are joined or connected by the edge AB if and only if that vertex set AB is a subset of the edge set. A little bit of vocabulary. If you have an edge connecting two vertices, say AB is an edge, then A and B are called the endpoints of that edge. We say that the edge AB is incident on the vertices A and B, and we also say that A and B, those vertices, are incident on the edge. If two vertices are connected by an edge, then those vertices are adjacent. Two edges are adjacent if they share a common vertex. So I'm just going to sketch a quick, really simple graph to illustrate what I mean here. So here's vertices A and B and C, and let's say I've got this edge and this edge. So here are these vertices and edges. Let's say I've got this edge, I'll label this edge E1 and I'll label this edge E2. We would say that vertices A and B are adjacent. Because they're connected by the edge E1. And then E1 and E2 are adjacent because they share the vertex B. We'd say that A and B are endpoints of E1. We would say E1 we could list as the two-element subset of the vertex set. Consists of A, B. Now, it's a subset, so it doesn't really matter the order in which we list the vertices. And E2 is the set B, C. In this example 4.1, they've given us a set of vertices. So we have 5 vertices, and they've listed out the edges, and we're just going to draw that graph. So when I start out a graph like this, I like to kind of just space them out evenly, give myself plenty of room to draw any needed edges. So here's A, B, C, D, and E. So we've got the edge AB, we've got the edge AE, BE, BD, BC, and CD. And those are all the edges. So here's that graph. We're not allowing, these edges are not directed. We'll look at graphs that allow directed edges later, but you'll notice that these are sets, right? So the order doesn't matter. The edge AB is the same as the edge BA. So in general with graphs, edges are either connected or they're not. Generally, we only allow one edge between two sets. If we allow multiple edges between two vertices, then we would call it a multigraph. Usually we don't allow loops, but if we did allow loops, we would call it a pseudograph. When we look at directed graphs, we'll see that with directed graphs, we usually will allow multiple edges and would allow loops as well. A subgraph of a graph is, first of all, a graph itself, and it just has to be taken from the vertices and edges that are already there. You can't grab an edge without also grabbing the vertices that are connected to that edge. So you can't have an edge that leads to nowhere, but you just take a collection of vertices and edges that were part of the original graph, and that's a subgraph. If we look at a vertex of a graph, the degree of a vertex is the number of edges that are incident on that vertex. If you have a vertex with degree 0, so a vertex with no edges connected to it, we call that an isolated vertex. So in this example, we're going to list the vertices that are adjacent, and we're going to identify isolated vertices. So adjacent vertices. So these are just vertices that are connected by an edge. So A and B, A and C, B and F, C and F, A and D, and D and F. Really, you get a pair, I just went through and just for each edge, I identified the 2 vertices that were connected to that edge. That gives me a pair of adjacent vertices. We could write out the degree of each vertex. So the degree of vertex A, which we would indicate in this way, DEG of A, degree of A is 3. The degree of B is 2. The degree of C is also 2. The degree of D is also 2, and the degree of F is 3. So these are the degrees of all the vertices. Notice that there are no vertices with degree 0, so that means that there are no isolated vertices. Here we're given a graph, and we're gonna draw a couple of subgraphs. So again, I'm just gonna make a graph by collecting the some subset of the vertices and edges that are already there. So maybe I'll grab vertices A, B, D, and E, right? So like this box over here. And then of those edges that are there, maybe I just grab this edge, and that's it. Right, so I can grab a vertex without grabbing edges that are connected to it. I cannot grab an edge without grabbing the vertices that are connected to it. So there's one subgraph. So maybe if I call this G, I could call this subgraph G1. And maybe I'll take another subgraph. Maybe I'll grab vertices B, C, and F. And this time I'll just grab all the edges. I cannot add edges that weren't already there. So I'm not allowed to add an edge that connects B and F because that edge was not already in the graph G to begin with. So here's a graph G2, and we would say G1 is a subgraph of G, and G2 is a subgraph of G. If we looking at the graph G, the one they gave us, right? If we just sort of jot down the vertices, so the degree of each vertex, the degree of A is 2, the degree of B is 3, the degree of C is 2, the degree of D is 2, E is 3, and F is 2. If we add these up, right? So if I take a sum, there's my summation notation of the degree of all the vertices in that graph. That gives us 4 plus 6 is 10 plus 4 is 14. We got 14. As it turns out, if you look at a graph, if you take any graph and you add up the degrees of all the vertices, it will always be even. That's our first theorem, and we're going to prove it. As you can see, it's not going to take a whole lot of work to prove this. You can see there's not a lot of room that I've provided for this proof. So here's how it goes. Basically, we prove this by considering the edges, right? So each edge of a graph has 2 endpoints. And that means that each edge contributes 1 to the degree of each of its endpoints. So now, if we kind of take this information and think about what does that mean about the sum of the degrees. So each edge is going to contribute 2 to the sum of the degrees of the vertices. And that gives us the following result, that if I add up the degrees of the vertex, of the vertices, where V can be any vertex, right? I let V range over all the vertices in the graph, and I add up all their degrees. This is going to be 2 times the number of edges. And that, of course, is even, which is what we wanted to show. Now, individual vertices could have degree even or odd, right? But as it turns out, in any graph, there is always going to be an even number of vertices whose degree is odd. You can have odd, vertices with odd degree, but there will always be an even number of them. And that's the next theorem that we're going to prove. So we're going to prove this by contradiction. So let's suppose that there are an odd number of vertices with odd degree. So if I add up the degrees of these vertices, that has to be odd, right? If you add an odd number of odd numbers, you're going to get an odd sum. So the sum of these, of the degrees of these vertices will be odd. Now the remaining vertices have even degree. And so the sum of the degrees of these vertices has to be even. No matter how many of them there are, I'm adding even numbers together, so their sum has to be even. And so now, let's take a look at the sum of the degrees of all vertices. So I take the sum of the degrees of these vertices with odd degree. We said the sum of those degrees is odd. And then the sum of the degrees of the remaining vertices is even. So when I add up the degrees of all the vertices, we have an odd plus an even, and that is an odd number, and that contradicts theorem 4.1. And that means that there must be an even number of vertices with odd degree. right, a couple more definitions. If we have a graph, we got some vertices and some edges, one thing that we can do is sort of traverse a path. You know, start at one vertex and use the edges to kind of make a path from one vertex to another. A path of length k is just a sequence of vertices that start at one vertex and end at some other vertex, you know, starting at, say, v0 and ending at vk. The length of the path is the number of edges that you have to traverse to get. So the path will always have more, you know, one more vertex than edges. A simple path is one where no vertex is repeated. And then we say that a graph is connected if there's a path between any two distinct vertices. So we have a couple of graphs here. Let's focus on the one on the left first. We'll note that this graph on the left is connected. All my vertices from v0 up to v7, I can get from any vertex to any other vertex by traversing the edges. There's enough edges there to get me there. Now let's say I want to get from v0 to v4, right? One way I could do that is to start at v0 and go to v1, then to v4. Oh, but maybe I'm not done. I'm going to go to v6, then to v7, then to v5, and then to v4. Right? So there's a path that starts at v0 and it ends at v4. And I would indicate that path just by listing the vertices in the sequence that we traverse them in. So v0, v1, v4, v6, v7, v5, v4. There's a path. It's not a simple path because I've repeated a vertex, and namely I've repeated the vertex v4. So anytime there's a path between two vertices, there will be a simple path. This is the theorem that's shown next. We're going to state it without proof. It's pretty I'm going to say pretty obvious. But let's say I take any path that is, this one is not simple because I could see that v4 is repeated. All you got to do is take out the, you know, it goes, here's where it gets to v4 first, here's where it gets to v4 second. Just eliminate that part. So the simple path is given by v0, v1, v4. I say that this theorem is pretty obvious just because once you have any path written out, you can remove redundancies. You can remove any piece that repeats. Now looking at this graph on the right, this is not connected. It's not connected because, for example, there is no path from v0 to v4 in this graph. And in fact, a graph that's not connected, it almost looks like you have multiple graphs there, right? I mean, certainly the triangle on the left and the line that's on the right in this graph, I could think of those. They are certainly subgraphs of the whole graph. But you can have, this can be your whole graph, and it doesn't have to be connected. There's some, you know, when I look at this and I say I've got these two different pieces, and those are, you know, we could almost think of them as their own graphs because certainly they are subgraphs. But these jump out as obvious subgraphs, right? The triangle on the left and that line on the right jump out as obvious subgraphs. And these types of subgraphs are given special names. They're called components of a graph. And a subgraph is a component if, first of all, it's non-empty and connected. So you have to have some vertices and edges. And the subgraph itself has to be connected. So I can't have any disconnections, right? I can't have any isolated vertices in a component. Also, in addition to needing to be connected, it has to be maximal and connected, meaning it can't be itself a subgraph of some bigger subgraph that's also connected. So I'll show you what I mean when I say that. This is a component, right? and this is a component. But look at, I could take a look at this subgraph here. The subgraph that's V0 and then V2, that's connected, right? It is non-empty and it's connected, but it is not a component because that subgraph that I've highlighted in green here is already a subgraph of a bigger connected subgraph. So that's what makes that triangle part a component, and this piece here, the part that's highlighted in green, that's not a component, even though it's connected and a subgraph. So we're just gonna, I guess we kind of already repeated these, but these are the components. Of that graph. All right, a couple more definitions. A cycle is what it sounds like. First of all, it's a path, and you have to start and end at the same spot, but you cannot repeat any edges in a cycle. So no edge can be repeated in a cycle. A simple cycle is one where you start and end at the same vertex, obviously, because it's a cycle, but that one vertex is the only vertex that's repeated. So no repeated vertices except for where you start and end. And a cycle already can't have repeated edges, so a simple cycle doesn't have repeated edges. When we talk about an n cycle, we're just talking about the length of that cycle, a cycle of length n, which is the number of edges. And when it's a cycle, because you start and end at the same vertex, there's also n distinct vertices. So you repeat the first, the starting and ending point, but there's still only n distinct vertices. So here's a familiar graph, right? We looked at this before. So let's say we're going to get a cycle that starts and ends at V0. Okay? And here's how I'll do it. I'll go to V1, and then V4, and then V6, and then V7, and then V5, and then V4, and then V3, and then back to V0. So there's a cycle. Notice I have not repeated any edges, so it is actually a cycle. Let me just write it out. V4, V1, V0, V1, V4, V6, V7, V5, V4, V3, V0. Okay, so that's a cycle. It is not a simple cycle, though, because we have repeated a vertex, namely, we've repeated the vertex V4. To make a simple cycle from this one, as we talked about with eliminating redundancies with the path in one of the previous examples, we're going to do the same thing. I could see that I'm repeating vertex 4. There it is the first time. There it is the second time. I only need to hit it once. So I'm going to eliminate that. Once I get to V4 the first time, I could just continue on with the rest of that cycle, V3, V0. So there's my simple cycle. V0, V1, V4, V3, V0. Okay, then we're going to finish this up by looking at a couple of special types of graphs. A complete graph with n edges, or with n vertices, is where you start with the number of vertices and you draw every possible edge. Every edge that could exist does exist in that graph. That's why we call it complete. So the complete graph with n vertices is denoted by Kn. So we're going to draw the graphs K2, K3, K4, and K5. So K2, I've got 2 vertices. Now with 2 vertices, there's only one edge I can draw, so there's K2. K3, I've got 3 vertices. I'm going to draw every possible edge, and that's all the edges we can draw. K4, starting with 4 vertices. So I've got those, and then I can draw a couple more edges. I can draw that edge, and I can draw that edge. And those are all the edges that can be drawn. And then K5, I need 5 vertices. And then I'm going to draw all possible edges. And there's K5, the complete graph with 5 vertices. Okay, the next type of graph we're going to look at is a bipartite graph. And a bipartite graph is one where you can kind of partition the vertices into 2 sets. And what makes it bipartite is that the only edges that exist go between the 2 sets, but not within the 2 sets. So for example, I'm going to just draw one right here up in the margin. Maybe I have, here's one, 3 vertices in one set, and maybe a couple of vertices down here. And I'm just going to draw some edges, but I'm going to make sure that they only go between the top and the bottom set and not like horizontally. So there's an edge, maybe there's an edge, maybe there's an edge. That is bipartite. What is not allowed is having an edge that goes within a set, like so between 2 vertices in the top set or between 2 vertices in the bottom set. Like, that's not allowed. A complete bipartite graph is one where you have 2 sets of vertices, right? So you have, I always draw them kind of one set on the top and one set on the bottom. And then what makes it complete then is you've drawn every possible edge that can go between the top and the bottom. We denote this graph, the complete bipartite, as K sub m comma n. So how many edges in each of the 2 sets. So let's draw some of these complete bipartite graphs. K1, 2. Well, I've got one set has 1 vertex, the other set has 2 vertices, and I'm going to draw every possible edge that can go between the 2, and that's just these ones. K2, 3. So one set has 2, the other set has 3. I'm going to draw all the edges that can be drawn between the 2 sets. And that's all we can do. K2, 2. Two sets on top, 2 vertices on top, 2 vertices on the bottom, and they can only go in between. So that's going to look like that. And then K3, 3. 3 vertices on the top, 3 vertices on the bottom. Drawing all possible edges between the 2 sets. Looks like that. All right, so that finishes up this first section. In the next section, we'll take a look at directed graphs.